In our last topic, topic 9, we looked at some circuit analysis, but we stuck to just simple circuits. In other words, all series or all parallel, not a combination. So what we're going to do in this topic, topic 10, is we're going to take a look at what it looks like or how you treat a combination circuit. In other words, what happens when some resistors are in series but others are in parallel in the same circuit. Okay, it makes it a little more complicated, but all the same skills apply. All the same tools that we use to solve the simple circuits still apply to the combination circuits. It just takes a little bit more thought. So remember, Ohm's law, that's the easiest thing to use if you can do it. Ohm's law of V equals I times R. Okay, we can use that anytime we know two of the three values. And if we organize it in a table, that's really easy to see. And I showed you that method last day. Okay, Kirchhoff's current law, which is current in equals current out, that's important, especially when there's a junction. If there's no junction, then the current doesn't change. That's easy. That's a series circuit. But if there's a junction, like in a parallel circuit, then the current splits. Then there's the voltage law that says around any complete path, the voltage rises equal the voltage drops. Keep that one in mind. And as an application of those two, an application of the current law is in a series circuit, the current has to be equal everywhere. And we know that because there's no splits, there's no junctions. It doesn't split off and go two different ways. But in a parallel circuit, voltage is equal in parallel branches. Okay? In other words, the voltage doesn't change in the parallel part. Okay, so you got to be careful. And remember your rules for adding resistors, because we do have to do this from time to time, and I'm going to show you some examples of this now in just a little bit. But in the series circuits, resistance is simply added up. It's cumulative. In other words, R1 plus R2 plus R3, however many resistors we have, but only if they're in series. Okay, if we have some parallel ones thrown in there, then we have to do it in two steps. And I'll show you what I mean by that in just a second. When we have parallel, you do the reciprocal. 1 over RT equals 1 over R1 plus 1 over R2, etc., like this. And sometimes you may have to combine two series resistors first before you can do the parallel one. Okay, so, and again, keep it organized by using a table. That's always good advice. Always good advice. So let's take a look at some examples now from old public exams involving combo circuits, combination circuits. So some of this is going to be multiple choice, so we'll look at some multiple choice ones first. Okay, here's one here. What is the current through the 2 ohm resistor? Well, what you got to realize is because the 2 ohm resistor and the battery are in series, then whatever the current is leaving the battery, that has to go through resistor 2. It has no choice. There's nowhere else for it to go. It doesn't split until it gets here. So we don't really care about that. When it gets there, it will eventually split. So what we've got to do is we need to find the total resistance so we can find the total current. So the very first thing I'm going to do is I'm going to find the total resistance. So here's what I do. I'm going to do this part first. So 1 over Rp, 1 over the parallel resistance, equals 1 over 66 plus 1 over 33. Okay, and when I do that, I get Rp equals, just watch, 1 over 66 plus 1 over 33 to the negative 1. In other words, I take the reciprocal of that. And if you like, you can do all that in one step in your calculator if you want to. That happens to equal 22. Now I can find the total, because the total is just going to be that 22 plus the 2 that's in series with it. So plus 2. So the total resistance is 24 ohms. Now I'm not going to bother to use a table here because there's only a couple of things we needed to find. Now I can find IT. IT is equal to VT over RT. Always use that if you can. I know that VT is 12. I know that RT is 24. Divide those and you get 0.5 amps. That's IT. But because the 2 ohm, look, if I leave here and come around to that resistor, there's no junctions, there's no nodes. The current has to go, all of the current that leaves the battery has to go through resistor 2 ohms. Has to go through that resistor, no choice. So the answer is B, because it's the same as the total current. Okay, same. So there's your total current. Therefore, there is the current through the 2 ohm resistor. So that's a fairly straightforward combination circuit. But in combination circuits, you've got to be careful finding the total resistance. That's the important part. That's the part that sometimes may be a little difficult. Let's try another one. This one would be a level 3 question. This is a level 3 question. Take a look. Right now, the switch is open. Now, with that switch open, bulb X is the only bulb lit. Bulb X is the only bulb that's on. X and Y, or sorry, Y and Z are not on because that branch of the circuit is open. It's off. Okay, so the only bulb on is X. Now, we want to know what's going to happen to the brightness of the 3 bulbs, X, Y, Z, when the switch is closed. Well, obviously, once the switch is closed, Y and Z have to get brighter, don't they? They have to get brighter. That's the only possibility. They have to get brighter because they weren't even on before. So right away, we know it's got to be either this or this. We can rule out A and D right away. That's impossible. Bulb Y and Z, you can't get any dimmer than off. Off is about as dim as you can get. So when you turn them on, they got to get brighter. So we know it's either B or C. Now the question is, what happens to bulb X? Does it get dimmer or does it stay the same? Now be careful. It's easy to say that now because there's 3 bulbs on, bulb X is going to get dimmer. But that's not the case. That's not the case. If you think about it, just think about it. When this switch is open, it's just like this part here. I'm just going to cover it up. This part of the circuit kind of doesn't exist at all. Okay, that part of the circuit really doesn't exist when that switch is open. So we've got this bulb has the same voltage as this battery. So because of that, we can figure out what the current is through that bulb. Because in that bulb, whatever the resistance of it is, let's say it was 10 ohms, that would determine the current going through it, right? I equals V over R. And the current through the bulb determines the brightness of the bulb. Okay, current determines brightness. So for that particular case, the voltage of the bulb is the same as the voltage of the battery. The resistance of the bulb is constant anyway, so I equals V over R. So that will give us the brightness. Then if we close that switch and take that away, the voltage in this bulb is not going to change because that bulb is all by itself on this parallel branch. So even though we add in these other bulbs, that's going to cause this voltage to stay the same as it was before because it's still parallel with that battery. That's still one possible path. So because the voltage didn't change and the resistance didn't change, then the current didn't change. And if the current doesn't change through that bulb, the brightness of the bulb will not change either. So the answer is actually C, not what you might think. Okay, you might think B because more bulbs means less current, and therefore less current means the bulbs are dimmer. But that's not the case. As soon as you add these other resistors on over here, that actually draws more current from the battery because the resistance decreases when you add on parallel resistance, right? Resistance decreases. But the total current going through this bulb, bulb X, actually doesn't change. The extra current just goes through the other part of the circuit. Okay, so that's a kind of tricky one. That's what we call a level 3. That's a level 3 question. A little bit tough. Takes a good bit of thought to that one. You really got to be careful. Okay, the first part was easy. Figuring out that bulb Y and bulb Z got brighter. They had to get brighter. They were off to begin with, so they couldn't get dimmer. You can't get dimmer than off. So that ruled out 2 choices. Then you had a 50-50 chance. But when you think about it, C has to be the right answer. Okay? Let's give this guy a try. Another combination circuit. We want to know the current through that 100 ohm resistor in that circuit. The current through the 100 ohm resistor. That is almost exactly the same as the first example we did. Okay? It's hardly any difference at all. In fact, the resistors are even almost the same size. In the first circuit, that 68 was actually a 66. That's the only difference. This came off a different exam, but obviously they probably just reworked the numbers a little bit. It's really essentially the same question. So let's go through it. My total resistance is going to be 10 plus the parallel part. And the parallel part goes like this. 1 over 33 plus 1 over 68 reciprocal. In other words, to the negative 1. So put all that together, and you get a total resistance of 32.2 ohms. 32.2. Okay, and the other difference, by the way, in the other one, there was a 2 ohm resistor instead of a 10. But anyway, there's the total resistance. Now I can find the total current because it's just V over R, VT over RT, which is 12 divided by 32.2, and the answer is 0.37 amps. That's the total current leaving the battery, but remember, that total current has to go through this resistor. There's nowhere else for it to go. It has to go through the 10 ohm resistor as well. So the answer is B. The answer is B. Okay, and again, that's not terribly complicated. Okay, that's a pretty straightforward, that's what we call a level 2 question. Pretty straightforward calculation, nothing unusual, nothing you haven't seen before. Okay, there's a little bit of work to it. It's more than one step probably, but it's not a difficult problem. Okay, if you know how to do circuits, that's pretty simple to do. All right, let's try one more multiple choice. Now this one's again is a tougher one. This is a level 3 question again. This is level 3 again. You really got to think about this. If a copper wire was connected across points X and Y in that circuit, what would the current through the bulb be? And what would happen to the brightness of the bulb? Well, what you got to remember is this. These two resistors are in parallel with that piece of wire from X to Y. So as soon as you put that piece of wire in there, the current is going to follow the path of least resistance, which effectively eliminates those two resistors from the circuit. That's what you call a short circuit. You've bypassed that part of the circuit completely. So by putting that wire in, you've really turned this into just a simple series circuit. All right, so the current, I, is going to equal V over R. V over R. So the V is 23. The R is 21. Those numbers are both given there. Like I said, when you put the wire, that effectively eliminates the other two resistors. They're gone now. They're not serving any purpose whatsoever because that wire has effectively zero resistance. So that's where all the current's going to go. Those other two resistors are going to be just like you took them out altogether, just like they weren't there. That equals 1.1 amps. So now we know that the answer is not A or B. That's actually what it was before the wire was put there. So now, did it get dimmer or did it get brighter? Well, let's just think about it. When the wire wasn't there, all right, without the wire, without the wire, there was more resistors, okay? And what it was going to be now, the total resistance would be 21 plus 1 over 15 plus 1 over 10 to the negative 1. Okay, that's the total resistance now, which is actually greater than 21. Right? It's actually going to be bigger than 21. So in other words, there was more resistance. Okay, this is with the wire here. This is with wire. This is without wire. I don't even need to calculate what it is. I know there's more resistance just by looking at the calculation. I'm adding something on to that 21. With the wire, the resistance is only 21. That's it. But when with the wire not there, those other resistors come into play, and the resistance is more than 21. So before the wire was there, with the bigger resistance, okay, the current was less. So without the wire, more resistance means less current. The more resistance, less current can go through. So if there was less current before and more current after, then obviously the bulb got brighter. The bulb had to get brighter. Okay? So if you know the bulb got brighter, then you know the rest of the problem. You know the rest of that problem. Okay? If the current got bigger, the bulb got brighter. It's as simple as that. Remember what I told you. The current going through that bulb is what determines how bright the bulb is. The more current, the brighter the bulb. Now, if too much current goes through, the bulb can actually burn out. Okay, but the more current you put through, the brighter it gets. And you've probably seen that before. You've done those little experiments in school before, back in elementary school, where you hook one battery up to a bulb. It's fairly dim. Then you put 2 batteries connected to light the bulb. It gets brighter. Okay, 3 batteries makes it even brighter still. Maybe if you went to 4 batteries, you actually blew the bulb. Okay, you may have done that before. But that just goes to show that more voltage gives you more current, therefore the more current, the brighter the bulb. Simple as that. Now, I'm going to stop there. We're going to do this in 2 parts. Okay, so we're going to go now, just to keep the file size from getting too large, what I'm going to do now is I'm going to pause, and we're going to do a second part here. The second part are going to be a number of long answer questions from part 2 of public exams, and we're going to solve some circuits. In other words, we're going to look at some of the circuit analysis problems that have been on previous publics. And like I said, every single old public has one of these. Okay, so they all have one. Therefore, that's one question that you'd better be ready for. So, part 1 done. We'll start with part 2.